Peyton, have you finished that bell ringer? Bell ringer. We have 2 more minutes to finish up that bell ringer. We got to get going, guys. Most of us haven't even really started.
That'll make you early. Oh, you gotta start up. I don't want to.
You know what?
There's not anything out of the book yet. It's the dream job salary task is where you should have notes about linear and exponential.
Why would you feel like? I feel like.
What are you talking about?
I never saw it.
I beat you better than him having the whole.
Let them go, boys.
There's 2 Okay, so.
By the way, guys, the other issue that I see for most of us is that we're just trying to look at the table without writing a single thing down. If you're going to try to write the equation of a line, what could you probably do first to help you start getting there? Yes, look at your notes, but also, where should we start if we're trying to write the equation of a line? Oh, could you write out the equation to help you start thinking about it? We forget the little details. What is the equation of a line that we should probably think about?
Why are you not so big?
Okay. Because if you write that out, that might help you because we should know how to calculate that thing called m, or the slope, which is also the, what kind of rate of change? Constant additive. So write it out. Like, write it out every time. Don't just stare at it and think it'll magically pop into your head. Use the basics. How do we calculate slope? No, that's the slope-intercept form of a line. How do we calculate just the slope? You should have notes in notes. Rise divided by run. I think I showed you another way to write it. If I didn't, a better way to understand it is the change in the y divided by the change in the x. Did we talk about this on Tuesday? Okay, so I'll quickly point, actually I'll talk more about that in a second. You can identify your rise and your run in that table by looking at the change in the y, right? Because if it's rising, which variable is that? The y, so it's how much the y changes. The run is how much the x is changing. So this is a slightly better way to write it. I'll talk more about that in a second. What do I mean by b? Y'all, it's the slope intercept, the y-intercept, meaning that we need when the x is what value? 0. And then the y-intercept. You've got 60 more seconds to get an equation in there. And then we're going to go over this problem. Start with the basics though. Write out that equation.
C.
Then we need to get something typed in. And if you're struggling with this problem, you should probably get out some paper because we're going to do some bell ringers and you're going to do some practice on Monday with writing the equation of linear functions and exponential functions. So I get actually a notebook paper to show practice with this. Madison, where's your sheet to take notes?
Right here.
You guys stop waiting. Alright. I'm stopping the poll. I'm going to show you how I would do this with the table. But I want you all to pay attention to this. Most of y'all think about slope as rise divided by run, right? Yes? A lot of us know that that's the y-intercept. What could I do with that table to help us think about rise divided by run and the y-intercept there? Does it have to stay in a tabular representation? Could I make a graph of this line? Take a pencil, put the pencil to paper, make a quick graph of this. This is an easy strategy to make sure that you are doing everything possible to get this answer right. So I've got 3, 1, 2, 3, 4, 5. I've got, what was the next one? 6, 3. So 6, 3. And then 9, 1. Is that right? And it keeps going beyond that, but I can just draw a line now through those points, even if it's a little imperfect. There's my line, and it's probably supposed to go through there. Okay, so now my slope, how much is it rising? How much is it rising? Down 2. How much is it running? 1, 2, 3. I know it's a little sketchy looking at the graph up here, but that's why you could have made your own graph to identify rise and run. Notice I could have also gone from this point up to this point, right? It would have been up 4. Either direction, it would have given me the same answer to the left 6, right? Negative 2 divided by 3. That's my rise divided by my run. That's the same as positive 4 divided by negative 6. That's it. Rise divided by run. Why are you looking at that like it's crazy, Elijah? Nothing? You good? Take notes on it so you can do this in the future? Guys, you cannot wait on me to tell you to take notes. Y'all are 10th, 11th, 12th graders. Huh?
I didn't know what I wanted to do. You know how to take notes?
It's interesting because, okay, but did you think about drawing a graph from the table to make the equation of that line? Or should you probably take notes as a reminder, hey, I can go from a table to a graph to get this equation? Okay. There's a reason why I'm going through this. These are notes. There are times when I took notes in college, not because I didn't know how to do it, but because I knew there's a reason why the professor's going over this. If I'm writing on the board and I'm telling you these things, it's because you probably need to know this. And so when I draw this out, I can identify the y-intercept easily. 1, 2, 3, 4, 5, 6, 7. And so my equation would be y equals negative 2/3 x plus 7. That's it. You are making this harder than you have to because you're not paying attention to what I'm teaching you right now. I'm teaching you how to do this efficiently.
Oh no, I was just trying to see why I didn't know.
Okay. Yeah. That's fair. So let's focus on this method. So, the other thing that I would point out, what I will say is, the graph is not the quickest way. It's probably the easiest because it's easy to see the slope, it's easy to see the y-intercept. You can also get graph paper to help with it, but it's not necessarily the quickest, but it is the easiest. All right? So, let's look here. First off, I need the y-intercept, right? Or I do need the y-intercept, yeah? Do I have the y-intercept in this table? Where do you see it? I thought I said the y-intercept was 0, 7.
It's not on the table.
It's not in the table. Now, can I get it from the table? Because what do I need for the x value? I need a... To have a y-intercept, the x value has to be 0. It has to be a 0. So I have a pattern here. What's happening to the x every time?
It's
Not doubling it. Right, you can't just look at one, you have to look at multiple. So what number do I have to, what could I put here? There's my 0, right? 0 plus 3 is 3. So I just have to extend the table a little bit. which means I now need the x value, or the y value. What's happening to y every time? Subtracting 2. So to go back up to here, what number did I need to have? 7 minus 2. Oh, and notice that also gives me my slope. Because we already talked about the fact that slope is rise divided by run, which I mentioned is the change in y divided by the change in x. You may be familiar with y2 minus y1 divided by x2 minus x1. Yeah, that's way harder than it has to be. If you're subtracting things, you're finding how different they are, right? How much they've changed. So this right here is the Greek letter delta. Whether you're in math or in science, that Greek letter delta just means change. And so there's the change in y. So how much is my y changing? Subtracting by 2. How much is the x changing? Is that the same slope that we saw earlier? The table, once you learn it, is definitely the quicker method. Okay? It's just learning how to identify slope and y-intercept. But this goes back to, we got to start writing out the general equation first and then identifying the pieces of that. You're making it harder than that if you don't write out the equation. I saw so many of us staring at the calculator like we were hoping it would magically pop into our heads. Stop doing that. Follow the basics. I write out the equation of a line to help me focus my attention. You got to know what the end result is in order to get the pieces to get there. Right? If I leave Hillcrest High School and I want to go to Pastor's Kitchen out in Northport, I can't just magically start driving around and hope I get there. I got to know where I'm going, and I have to have a path to get there. I know that I'm going to go out Patriot Parkway. I'm going to take 69 north till I get to McFarland, take a left onto McFarland. I have a path to get there. I've got to know my end result if I want to know the pieces to get there. So start with that equation. Y equals mx plus b. Okay, so slope, I need that piece. Rise divided by run, or the change in y divided by the change in x. B, the y-intercept. Okay, that's when x is 0. You got to know those pieces. I'm going to pause for a couple minutes, let you take the notes that you need to finish taking, and then ask the questions that you need to ask. But learn this. Math doesn't just magically pop in our head. We got to know what the end result is. I want the equation of a line. Cool. So how can I get there? Okay. Don't worry about this yet. I'm going to talk about it briefly before we get started. It looks like most of us are done taking notes on slope-intercept. If you're still taking notes, continue. But I'm going to talk about this equation up here. There's another form for the equation of a line known as point slope. This is even easier than slope-intercept sometimes, because what do you have to have in order to get the slope-intercept form? Huh?
Coordinates.
Not just any old coordinates for slope-intercept. Which coordinates do you need for the slope-intercept? You're not wrong.
Intercept.
The y-intercept, right? And not just any old intercept, it has to be the y-intercept, right? But like originally, did I have the y-intercept of that equation? No. I found it, sure, but this point slope right here is a little bit easier. The slope is still the same. Notice what is happening between the slope and these parentheses? Being multiplied, because multiplication is repeated addition, right? That's that constant additive rate of change for a line. x1 and y1, they both have that subscript of 1, meaning that they go together as any point, right? And so, I only wrote this red one here because I'm pretty sure that's what most of y'all are used to. Yeah, I don't know why teachers teach that one. It's fine, but watch what happens when I add y1 to both sides. Create that 0, and I'm left with this equation. This equation can be plugged into a calculator immediately without any extra work. Sometimes some people put that y1 first, but I'm going to just pick a point, right? What point should I use? Just give me one. 6, 3. Okay, so my slope is still negative 2/3 times x minus 6 plus 3. Okay, we good there? That's it. That's the equation of a line. Or that's an equation for that line. I'm going to come over here briefly because I want you to see something with that equation. So I can distribute, right? What is negative 2/3 times x? Negative 2/3 x. Negative 2/3 times negative 6. We got calculators if we're not sure. You have a calculator. There you go. Don't forget, because this will make your job easier, that negative 2/3, what does that fraction bar really mean? Division, so you can literally just type in negative 2 divided by 3 times negative 6.
Is it 4?
Is it negative or positive for it?
Positive.
Notice it's a negative times a negative, so it is positive, okay? I will show you a really quick little detail that's fun, because this can help you do this in your head. What's 6 divided by 3?
2.
What's negative 2 times negative 2? 4. Division first. That's again why I want you to recognize that that fraction bar is division, because if you do the division first, it makes doing the multiplication really easy. Make numbers smaller before you make them bigger. So you can do that in your head, but plus 4 plus 3. I simplify now by adding my like terms, and what do I get? Is that the same exact equation that we got earlier? Negative 2/3 x plus 7. So it's the same exact line. They were different forms of that equation of a line, but it still works. And so you need to know point slope and slope intercept. If you're going to write the equation of a line, you got to know those equations first. Make sure you note that these are just different forms for the equation of a line. But we got point slope form of a line and slope intercept form of a line. Okay, what are your questions at this point? And I'll look at this in a second to figure out what happened. Well, first off, your slope's off. That was the issue, yeah. Because you just looked at a point, you didn't look at the change in y and the change in x. That was the issue, yeah. All right. Questions, comments, concerns, pushbacks? Mr. Kinney, why are you this way? I already noticed Alita thinks that way, it's okay. Elijah too, I know. It's okay, Elijah, I still know you're capable, even if you don't believe it yet. I'll help you be convinced otherwise. Guys, I need y'all to understand, being capable doesn't mean that you master it right away. Being capable means that you can master it moving forward. It's about growth, not perfection immediately. That's one of the worst things that happens to students. I'll answer your question in a second, Max. One of the worst things that happens to students is we start to believe that my intelligence is defined by getting it right away, and that's not true. Hard work pays off. I've learned a lot over my lifetime, which is why I know as much as I do. It didn't come overnight. I'm 31 years old. I've been studying math like this since I was 14, 13, somewhere in there. I think I took Algebra 1 7th grade, Geometry in 8th grade. And that wasn't because of me, it was just because my school was crazy. And I loved that school, but they were crazy teaching Algebra 1 in 7th grade. Okay? Hard work pays off. Max, what's your question?
Isn't there a third form?
Standard form. There's actually a fourth form as well, because standard form, that's this one, ax plus by equals c. That form is really useful for word problems. because that multiplication right there, multiplication is repeated addition. That multiplication right there is repeated addition. And so that form is great whenever you're dealing with word problems where we see two different things changing at a time, right? So we have water being poured in at a certain rate over a certain number of minutes into a pool, and then it's being drained, or something like that. You have a certain number of adults on a field trip and a certain number of kids. Well, we don't know how many, but we have groups of each. Well, there are two different variables there. So repeated addition for those two different groups. Okay. There's an even more useful form of this, though. I don't remember the exact notation, but what it is x divided by the x-intercept plus y divided by the y-intercept is equal to 1. I didn't learn about that form until recently, and I was like, man, that's crazy cool. But it always works as well. So that's the intercept form of a line. That is not traditionally taught, though. Like, I literally hadn't seen it until probably 2 years ago. And I want you to note that. See how I said, as a 31-year-old, I didn't learn that until 2 years ago? There's always more to learn. Keep growing and learning. Stop looking for perfection right away. It takes time, it takes practice. Okay. I'll get off my soapbox about that for now, but I will always come back to it because it is still true. All right. We're going to do the Venn diagram for linear, exponential, and quadratic functions to start today. And we're going to do the introduction to Mathia so that you know how to use it for Monday and Tuesday. Key Anthony, I'm talking, bro. Thank you, sir. So I want you to hear me very clearly on this. The Mathia stuff that's online, by the way, quick show of hands if you have your iPad with you today. Okay, so there's at least a few people in every group. If you don't have it, look on with somebody. Mathia has been broken, or got broken yesterday in the nicest way possible. The IT department downtown is doing updates for other things, and it's screwed up Mathia, so I can't do anything right now. I'm hoping over the weekend that it gets fixed, but I'm going to also make paper copies to help you practice writing the equation of linear and exponential functions when Miss Estel is here. We'll see how it goes. So I will make paper versions of everything so that you can still get the practice that you need. But hopefully Mathia works. If it doesn't, I'll at least show you what it should look like. It's not going to work today, but I've heard that y'all might be able to log in still because one of my friends out in Northside tried it yesterday. It's a mess. But I'll at least show you from my perspective what it looks like. So if it's working Monday, you can take advantage of it. And then we're going to get into the textbook, Volume 1, Lesson 3, comparing multiple representations of functions. As a quick reminder, and we've started to already see this very heavily with linear, exponential, and quadratic, what is math?
A language for patterns and relationships.
Language for patterns and relationships. That's what we're doing. We're studying patterns and relationships, and we're putting a language to it. Now, that does mean some of us are going to have to study because we don't remember those patterns and relationships right off the top of our head. But go back and look at your notes. That also means we need to take quality notes. I've noticed that some of us are not taking all the notes that we should. If you look at your linear and exponential and you're like, man, I feel like I don't have a whole lot here, you might want to go watch the videos. I haven't posted yesterday's yet. I'll do that during my planning. But I'll make notes about when the whole class discussion is because it's really only 20 to 25 minutes of each lesson at the end where we wrap up what we have discovered. So go watch those 20 to 25 minutes and make sure that you have quality notes for what makes linear, linear, what makes exponential, exponential, that you know what the equations are, that you know what the rates of change are, what the shapes of the functions are on a graph, all those things. It's patterns and relationships, that's all it is. But yes, it is going to take time, it's going to take practice, and it's going to take studying. You got to do those things. Okay, so let's look at the Venn diagram here. I will say this. It is easier to work from the inside out because right here is something that would only be true for what type of function? The exponential, right? You might have to write small, you might even have to write out here and make a note that it's in the very center because there's quite a few things that we could put in the very center of this. Who has one thing that we could put that is an overlap between all three functions? Emma?
Constant rate of change rate, substitute variables.
Okay, so does anybody want to add on to that or push back on that idea that all three have constant rates of change? or that we substitute in for variables. Okay, I will say this. We are looking at the relationship between inputs and outputs. That's our variables, right? All of them have inputs and outputs, and all of them with those inputs and outputs are called functions. We're going to discover or look at in the textbook what makes a function a function. But part of the goal of this was that we look at our notes a little bit more, because I will say there's one of these functions that does not have a constant rate of change. Does anybody know which one it is?
Exponential?
I think exponential has a constant multiplicative. It's a constant ratio or constant factor, but it is a constant multiplicative rate of change. There's a different one. Quadratic has what type of rate of change? A linear, not constant, linear additive rate of change. So I'm glad you brought that up so that we can correct misunderstandings, right? It's great to make mistakes so that we can learn from them and make sure that we don't hold on to those moving forward. I need you to understand you can't be scared of sharing your ideas. I'm glad that Emma shared that idea, because that, I'm sure, is something that multiple people thought. We need to address that so we can fix it, right? She had a great point. We have functions, but we also need to learn, okay, they don't all have constant rates of change. But it does give us a good place to put something else. What overlap could we put constant rates of change? Oh, that's a great place to put that, right? They have different types of constant rates of change, but they both have constant rates of change. They have different types of constant, but they do both have constant rates of change. That was something that we would want to notice. Okay? Anybody have another overlap for all three, though? I saw at least one other person in class already that had a good overlap for all three. Madison, is that hand raised?
Yeah, it can be graphed.
Okay, they can be graphed, right? All three can be graphed. That should open it up to two more things.
No, I ain't sure. I didn't think that one.
Well, they're not all lines, but they all three have graphical representations. They all have tabular representations and algebraic representations, right? That's the thing for all three of them. And so overlap for all three can be converted among algebraic, graphical, and tabular representations. And so again, this might be why you need to move off to the side and add extra details for overlap of all three like this. And again, we're trying to create the equation of a line, and I gave you a table earlier, but could you create a graph to help that process? I'll go ahead and tell you, creating the equation for an exponential function is tough off of a graph. Much easier off the table. So think about going between different representations to try to get to the equation. And don't just stare at it, write stuff down. There was one other person though that had an extra detail that I actually hadn't even thought of. I noticed it when I was going around to glance at how we were doing. I don't remember who it was actually off the top of my head, so I hope they're willing to share it. But someone who had an overlap that we haven't discussed yet. I guess we're just going to miss out on the detail because I don't remember off the top of my head. Come on, stop being scared. Okay then. Moving on. If you realize that, hey, I need to add this in, then let me know. But guys, anyways. Let's look at overlap. Is there any other overlap between linear and exponential functions that we've noticed? Linear and exponential. Okay, so no one wrote any other details down? Yeah.
Don't all randomly have a function?
Like an f of x. So yeah, noting here that they're all functions is identifying that. Yeah. No, it's a good question, right? I would have just lumped it in under that. Okay, let me ask you this: linear and exponential. Yes, there are multiple ways to write each equation, but the two equations that we wrote before both involve, or so the original linear y equals mx plus b and y equals a. So y equals mx plus b and y equals a times b to the x. What are the two things needed for those equations? Well, yeah, they both need a variable, but there's something else.
Multiplication?
Well, kind of.
B.
Say again.
B.
Okay, which b? This one or that one?
What's the
They're the
difference?
same.
Everything.
One has an
The first
exponent and
one.
one doesn't.
The one with no exponent.
Okay, so what is this one with no exponent? That's the what of that line.
Y-intercept.
That's the y-intercept, right? But look again at this b, and so this is an important question, Sleet, of what's the difference? Notice how that has an exponent of x? Because an exponent is repeated what? Multiplication, right? So that's the y-intercept. That b is it's repeated multiplication, so it's the what?
X.
Addition.
No.
Rate of change.
Thank you. Good grief, y'all.
You're losing it.
We got the y-intercept, but that's a rate of change. Hey, what is this slope right here?
Ooh, rise divided by run.
Yeah, that's how we calculate it, but what is it? It's the
Slope.
slope, which is
The slope.
the slope, yes, but which is the...
The line.
Rate of change.
Thank you.
You could have just said it.
You could have just said that. I might have taught that already. Okay, so, look guys, I need you to hear me very clearly on this. These equations tie back into just the meaning. Multiplication is repeated addition. So remember, a line has that constant additive rate of change. So the slope is the rate of change. It's multiplied, repeated addition. But here, an exponent of x is repeated multiplication, and so that's the rate of change. So this was the y-intercept. What's this a here?
The y-intercept.
That's the y-intercept. So what are the two things needed for those equations?
Y-intercept.
Y-intercept.
Rate of change.
Oh! So we need the y-intercept and rate of change for basic equations. Notice how I say basic. There's not a whole lot going on there, but it is the most basic form of those equations. You need the rate of change and you need the y-intercept. Those are things we want to notice. We need to know all those details. The deeper you understand these functions, the easier it is to pull this information out. So let's look at the relationship between the overlap between exponential. I don't think there's anything else for exponential and linear, but if anyone sees anything, let me know. Exponential and quadratic, is there any overlap when we look at those different representations? Okay, so standard form does involve exponents. Well, let me clarify that all the different forms in some way involve an exponent, because, so here's the vertex form that we haven't looked at yet. Notice, it's squared. If I take the factored form, which again we'll study this more moving forward, if I take x times x, that's also x squared. And so they do both have exponents. Now there's a key difference. With a quadratic, the exponent is a... What's the exponent for a quadratic? Why are you looking at me? There's an example up on the board. 2, thank you. The exponent is a 2 for a quadratic. Exponent.
I got it.
Right? Okay.
I got it.
You look at that standard. The highest power is a 2. Okay. But what is the exponent for an exponential? A variable, okay? So I'm going to hold off on that just to show those differences. I'll say this. How about we think about a graph? What do exponentials and quadratics have in common that's very different from a linear?
They don't have lines.
They don't have lines, they have curves. That's an easy thing, right? It's identifying what is in common and what is different, guys. I need you to understand, like, you don't have to have it perfect, but I need y'all thinking about these things because we should recognize that quadratics and exponentials have curves. Notice, again, we're looking for patterns and relationships, finding out how these things are similar. We want to note those things. The similarities really help us understand them better, and it's the differences that really define them. What's similar between a quadratic and a linear? Well, graphically, they definitely don't look the same, right? No? I did think about one more similarity between linear and exponential. We'll come back to it in a second. But what about in tables? Was there anything in the table that was similar for linear and quadratics? Were they both constant additive? Constant additive? Okay, so they eventually got to be a constant additive, but remember, linear was straight up constant additive. You got to remember with a quadratic though, so here's an example of a quadratic. This is just literally y equals x squared. So the rate of change is always within the first set of differences. And eventually, yes, we got to a constant additive. But this is my rate of change. So it's not constant additive, that is called linear additive, but what do they both have in common? They're both additive rates of change. So great note on the idea of additive, and yes, this eventually gets down to constant additive, but that's how we know that the rate of change is actually linear additive. But they're both additive rates of change. That idea of an additive rate of change is going to define the entire function of what, or entire family of what's known as polynomial functions.
So if a linear is constant additive, and then quadratic is linear, which is constant additive.
Well, but remember, the first set of differences is the rate of change. So we get that this is linear additive right here because this is constant. Constant additive, what type of function had a constant additive rate of change? A linear function. But that tells us not that this is a linear function, it tells us that it's a linear additive rate of change. The rate of change is only what shows up in the first set of differences. The rate of change is only what shows up in that first set of differences. What do you have trouble with on that?
Oh, it's not trouble because I don't know. I just feel like it's unstable.
Why is that stupid?
Like they're the same thing, but not the same thing.
Well, okay, so I want you to hear very clearly on this because it's actually a good point. They're the same thing, but they're not really the same thing. That's why they're known as a family of polynomials. There's a huge similarity between them, and that's what we want to look at. The next power up would be y equals x cubed. X and y, negative 2 cubed is negative 8, negative 1 cubed is negative 1. You don't need to take notes on this, but I want you to see this. So, negative 2 to negative 1, that's adding 7. Negative 1 to 0 is adding 1, then adding 1, and then adding 7. So subtracting 6, adding 0, adding 6. Adding 6, adding 6. You see how that's constant additive right there? That means that this is linear additive. And so what rate of change does it have? What type of function had a linear additive rate of change? Quadratic, so what type of rate of change is this?
You just said.
A quadratic,
I was going to say it, I was saying.
quadratic, additive. rate of change. So it just keeps going based on whatever the power is. So again, you don't have to write that note. That's actually something we're going to study later. But that's the idea, is that the higher the power is, the more it takes to get to that constant additive. But that's what defines the function, right? Constant additive, so linear, so quadratic additive rate of change, so a cubic function. So if it was x to the fourth, any guesses what type of rate of change it would have? Y'all,
It'll be constant.
y'all, quadratic had a linear additive rate of change, right? A cubic had a quadratic additive rate of change. Notice how quadratic is x squared?
So linear.
No, because linear additive was quadratic. Remember, linear is x to the first,
Exponential.
not exponential, y'all.
Linear.
No, it's not.
So how we gonna know? What was
So
the
I
question?
want you to notice, look at the pattern. When it was quadratic, it was linear. When it was cubic, it was quadratic. So when it's x to the fourth, what's the rate of change?
So it's not linear again.
4.
Say it louder, Samaya. It's a cubic additive rate of change. It's always 1 power less.
That's weird.
Yeah, that is.
Yeah, that is.
How is that weird? It's a pattern. Look at
What
it.
pattern? Where did cubic come in?
Well, a cubic came in when you studied Algebra 1, hopefully. But I'm just trying to extend this idea. Like, we need to notice that there's a pattern. If it's quadratic, had a linear additive rate of change, 1 power less. When it is cubic, it has a quadratic additive rate of change, again, 1 power less. When it's, that's called quartic, x to the fourth, it's got a cubic rate of change. So let's say that I was looking at x to the sixth. What would the rate of change be? X to the fifth. Yeah. Rate of change would be x to the fifth. That's known as a quintic.
What about what's the word for 6?
No idea.
I'm out.
For the rate of change. Y'all, the rate of change is always 1 power less. Always. If it's a polynomial. Alright.
Why does it go back?
That goes into the idea of calculus to really explain why, but it's more like if you just look, guys, look right here. Stop and look. When it's quadratic, when I look at those differences, you see how this is constant additive? Right?
Yeah.
What type of function had a constant additive rate of change?
Linear.
Linear. So this rate of change is linear additive. Boom. So when I get to a cubic function, I look at those differences. I haven't found a constant yet. Still haven't found a constant. Here's constant. What type of function had a constant additive rate of change?
Quadratic.
Linear. That hasn't changed. What comes after a constant is linear additive. So this set right here is linear additive. If you were to graph those points, it would give you a line. Okay? It's a constant additive rate of change for here, so that's linear. But what type of function had a linear additive rate of change? Quadratic. So what's this rate of change? Quadratic additive. So you find your constant, and it's always 1 power up. So this additive rate of change is quadratic additive.
You made me miss elementary school.
You're in high school.
I wish I wasn't.
I wish I would back. I would go back.
I'm sorry for your sake. Yes, Max.
Is the quadratic function the product of 2 linear functions?
Yes.
That's so smart.
Can we just see next
How about that?
It does. But it's not. Look, even if you hadn't just thought about it, look right here. This is the factored form. That is linear, right? That is linear. It's the product of 2 linear functions. They're all tied together in different ways.
You ain't gonna make us like do it like that, right?
What is do it like that? I don't know what you're saying. We're not on a cubic function yet. We're on quadratic. Yes. Because I'm trying to make sure that you understand what that rate of change means.
Exactly. They trim out Mr. Kim.
Golly, y'all stress me out.
Trim.
You stressed yourself.
That's my job as a teacher.
Tom, you
If I'm not challenging you to think, then I'm not doing my
But
job.
I mean,
I'm not capable of doing this.
I mean,
That's a lie.
This is my argument. I feel like as a student, it's our job to challenge you to challenge us. So like, we gotta think about this stuff, and you gotta make us think about this stuff. But when we get it wrong, you gotta keep,
3 days.
you know, keep going.
And what did I do? I did.
No, if you get it wrong, you make it hard.
But like, it's
That's
our job to
not
stress you out. Like, it's our job to stress you
Y'all,
out.
let's get back to this. We're about to move on to the next thing, Madison, because I'm having a whole class discussion, not a Tory Madison discussion. Thank you. I didn't make it harder. I showed you an extension that shows the same thing. What we want to recognize is that the rate of change is always 1 power less. I can't just keep doing the same function over and over, but I can show you the next one to show, oh man, the rate of change is always 1 power less than the function itself. Now, we need to get back to filling out these things. So what is something that is unique for a linear function?
It's a line.
Okay, so the graph is a line. You can draw a quick example.
It shows in the first set of differences.
Hold on 1 second before that. Before we say that, what's another form that a line could have right here? Instead, what kind of slope would this be?
Increasing.
So it would be a positive slope. We could also have a negative slope, decreasing. Okay? Yes?
How can you explain like why the one going like this way
But a laser what?
So
Why
if
would
you
that
do
one
look
be
at
positive?
rise, it's going up, so that's a positive,
Okay,
and going to the right, so that's also positive.
okay. Thank
And a positive divided by a positive is positive. You can even go backwards, right? But if you go down, you're also going to the left, and what's a negative divided by a negative? Also, no?
Positive.
Positive, right? A negative divided by a negative is a positive. And you can look at the same thing here, right? If you're going down and to the right, a negative divided by a positive would be negative.
Thank you.
So that's a good question. Okay, what else is unique about a linear function? I heard someone, Malaysia, what did you say with it? Did you say something about a linear? That's a lie. Who was it?
See? It was her fault.
Salita? What did you say then, Salita?
Took too long. I think I said something about the first set of differences.
Yeah, the first set of differences is constant additive.
Okay.
Constant additive rate of change called what? What's the name of that constant additive rate of change?
We was already linear.
Linear?
The constant additive.
Quadratic. No.
Teachers, at this time, we're gonna start in small groups of people picking up iPads and.
Oh, I need to give me a sheet, man.
The constant additive rate of change is called the slope.
And that's alpha through delta. Thank you.
What grades? Sophomores, A through D. So slope is rise what? Divided by run equals the change in y divided by the change in x. What else should we know about linear? Slope intercept is y equals mx plus b. We also learned about the point slope, y equals m times x minus x1 plus y1.
And can we like put the formula, the linear function formula?
What do you mean?
Wait, f of x equals e plus m times x.
Oh, so that's the same thing as this, just flipping it, and you can always put f of x in for y. Yeah, so if you want to put f of x in there for y, you can totally do that. You could even just say f of x equals y equals mx plus b, showing that f of x and y are the same. Okay, so exponential functions.
Did I say multiplicative rate of change?
Okay, constant multiplicative. Who was asking, Malaysia? Okay, constant multiplicative rate of change. I don't remember if I told y'all the name of this. I think I did for third block, but I can't remember for y'all. But it's called a constant factor. Because you multiply with factors. Bless you. the name for an exponent, or the name for the shape of the graph is literally called an exponential curve. That's it. I thought there'd be something fancier. There's not. So, notice how if you move from left to right, how it's going down here for the right-hand one. So we would call that an exponential decay. And this would be an exponential growth. Please note that it does not actually touch the x-axis, much like with the standard normal curve, it approaches but never touches.
Are we gonna be working with absolute value this
At some point. Why? Okay.
year? Are we gonna be working with?
Absolute value functions. Okay. Any equations that we have learned?
What did they say? On the first chart.
Where? Here?
Yeah.
Exponential growth.
I ain't putting glasses on, so don't ask me.
Max, you have a question?
F of x equals a times b to the x power.
Okay, so f of x equals a times b to the x power. And you need to be careful that b is not the y-intercept this time. That b is the what? The rate of change. A, remember, is the y value of y-intercept. B is your constant factor. And again, go back to what those operations mean. The fact that there's a variable of x in the power is what's telling you that it's a constant multiplicative rate of change. The fact that there's a b or an x in the power tells you it's a constant multiplicative rate of change. A less common form of an exponential would be this. It ties into what we did with point slope earlier, and this will help you. Notice that's just the y value of any point, and there's the x value of any point, just like when we had this point slope form. So we have x minus x1. So that allows you to use any point, not just the y-intercept. B is still the constant factor, it's the base, but that is any point that you can use. Same. I hate a lecture like this, even when it's whole class discussion. Well, it's a weird thing that I'm going to test you on these ideas, so it's probably a good idea if you have a single place to look at all the notes for all these concepts. You can go back to your notes that you made elsewhere to help, but we need all this information in one place to succinctly study from. Quadratic functions, what do we, yes, Madison?
Parabola.
Parabola is the shape of the what? Graph. And it can either be concave up, or it can be concave down. So concave down, concave up. Does anybody remember what this point right here where the minimum or maximum is, what that's called?
Oh my
This, I don't know if I mentioned this earlier, but you should have seen it
We
in
talked
algebra
about
1.
this.
No, we didn't mention that.
Starts with a V.
god. Vertex.
Vertex,
Yeah.
right?
Don't you just let us see yours?
Politics.
Are you proud?
I am proud that y'all remembered something.
Thanks.
Sorry, that was rude. I'm sorry for the way I said
Thanks for
that.
minimizing our capability.
Yeah, I'm not minimizing it, but y'all been struggling to remember some of these things from Algebra 1. And that was rude of me to say it that way. That's my bad.
You're right. 2
Was it?
years ago. Yes, 2 years ago.
See, this is why I'm glad that we switched the order so that's geometry, Algebra 1, Algebra 2 now. Salita?
Was it 2 years ago?
Yeah.
I took it at 8
No,
grade.
we talking about.
Oh, yeah, still. I mean, that's how we had it, but
So what
That's
you
why
had
a lot of
last
times,
year?
hey, Canton, focus. Selena, what's your question?
I'm in the 10th grade.
I was gonna
Okay.
just make sure your name was Mr. Kenny, because I forgot.
What we forgot?
I can know all of your names, but you forget my name of Mr. Kenny? Like,
You
dang.
forgot my name one morning, and I didn't talk to you.
One morning, week 2. We were less than a week into school.
You still should know my name. Now, I was very hurt.
You can't remember me out of 4 teachers 4 weeks in, and you wanted me to just make sure I had you memorized.
No, I had to make sure I was correct. I know
So,
your name.
sorry guys, if y'all didn't know, math, algebra 2 and stats is all about Selena. So, I'll keep that in mind moving forward,
Thank
y'all as well. Alright, so what else should we know about a quadratic?
So linear attitude.
Linear additive.
Ready, Jane?
Yeah, that.
Oh, so we can know. Ooh, go Selena.
Alright. And there are, hey listen, there are 3 equations that we're going to study very heavily starting next week. There is the standard form of a quadratic. There is the factored form. And there is the vertex form.
I mess with standard form. I'm about to cry just looking at it.
You don't you dare. Why would you cry about it? Have we
See,
studied
that's
Stop.
what stresses me out.
Stop. Guys, we're gonna spend 2 solid weeks on just quadratics. Get over yourself. You got time to learn it, okay? And the reason why I'm giving this to you is because you should definitely go ahead and at least start looking at these forms. You don't have to know them perfectly. Which one do I need to write over there so you can more easily see it? Simon? The first 2, standard and factored?
I can see the standard. I can see the standard.
So this is standard, this is factored. X minus r sub 1 times x minus r sub 2. Subscript 2, huh? That's vertex form. H comma k is going to be the vertex, but we haven't looked at vertex form yet, y'all. That's my vertex. The k is the what part? Is that x or y? That's the y value of the vertex. Don't make it hard on that. You know, that's an excellent question that I don't know the answer to. I gotta try to look it up, see if there's a reason, but that's traditional when using what's called transformations of a function, h and k, for the translations. Okay. So this is a massive summary of all things linear, exponential, and quadratic that we should refer back to when studying for understanding checks, when working together to help each other understand these different things, when doing homework assignments on linear, exponential, and quadratic, stuff like that. And please hear me very clearly, quadratic is the one I know that we know the least. That's okay. If you are already done taking notes on that stuff, go ahead and put it in your notebook in order behind the dream job salary and the gold rush task. And I would put those things in order. Get your iPad out if you have one. If you don't have one, look on with somebody. And go ahead and pull up Clever on your iPad.
It's smart.
Once you get logged into Clever or hit the Clever app, hey guys, there should be a Clever app on your iPad. Look for a Clever app. Yeah, click on Clever. When you get into Clever, you should be able to find, oh, that's a whole lot of stuff written on that board right now. Okay? You need to be looking for this CL Carnegie Learning. You may have to click on, I think it's called District Apps or something like that at the top.
I don't have a clue.
District or share with me.
Maybe that's what
Then go on